Good day, ladies and gentlemen. This is our second discussion on Physical Sciences Grade 10, Term 2. Previously, we spoke about covalent and ionic bonding, and today we are going to briefly discuss crystal structures. To start off with this, we are going to talk a little bit about metals. Now, metals are pretty much made up of the metallic atoms sitting in what we call a lattice. And the electrons of these atoms sort of move in a very delocalized fashion between these atoms. So we refer to this as an electron sea, because you more or less have a sea of electrons all over with the atoms sitting in between. Now, this movement of electrons is what also makes metals such excellent conductors of electricity. Now, the reason we left metals over for today is because metals are a very specific type of lattice. The first type of crystal that we get, or the first lattice that we get, is a covalent crystal, a covalent lattice. This is named as such because the bonds between the atoms that make up this crystal is covalent bonds. An example of this would be something like a diamond. You then also have ionic. Ionic crystals are made up of atoms bonded together in ionic bonds. I apologize. Salt would be an example of this. Now, what is very important to note for these two is that covalent crystals, molecules in a covalent bond, in a covalent structure, share the properties of a covalent bond. That is to say, a high melting point, a high boiling point, etc. Same with ionic bonds. They share the properties of the ionic bonds. We also have a molecular crystal. These are crystals that are held together not by covalent or atomic bonds, but by intermolecular forces. An example of this would be water, H2O. Now, these intermolecular forces, that is to say that you have, in our example of water, an oxygen and two hydrogens. And these molecules have a charge, positive and negative. And positive and negative attract each other, which means that these molecules are attracted to each other. So it is an intermolecular force that holds these molecules together, and accordingly the crystal. Now, obviously, water, as we perceive it, is a liquid and as such not a crystal, but of course water can freeze. We are talking of solids in this instance. And snowflakes, ice crystals, those are molecular crystals. Now, the final type of crystal that we have is a metallic crystal. Now, as I have stated already, metals are rather unique in the sense that they have this electron sea, and metallic crystals, obviously, are then crystals made up of metals, individual atoms packed together very closely with the delocalized electrons moving between them. Oh, excuse me. If you have been in a situation fortunate enough to actually see pure metal crystals, you might know that they are actually quite beautiful. A very nice example would be something like pyrite. It is iron and lead, if I'm not mistaken, and it forms perfect little cubic crystals. So these crystals can in some instances be rather beautiful. Now, the reason we are talking about crystals and about these crystal structures is not so much to talk about how beautiful crystals are or about pyrite, the metal, anything along those lines. It is because we need to talk about how we view, how we represent these elements, these atoms. I have a little model here representing water. Now, if we talk about water, I can say water. That, in and of itself, unless you actually know what water is, will mean nothing to you. If I tell you water is H2O, now I tell you that we have hydrogen and oxygen, and I also tell you how much of each. Obviously, 2 H's and 1 oxygen. I can then also go on to tell you that the crystal structure, or the way that the molecules or atoms are connected, is that we have 1 and 2 other ones sitting like that, with that one being the oxygen and those 2 being the hydrogens. Now I can continue on to tell you that the reason it sits like this and not in a chain like that is because oxygen has some extra electrons that are sitting over here, and those electrons push the hydrogens away. But in essence, this diagram or this model tells us how this molecule looks. And that is the reason that we are talking about these today. There are a few things that you need to know when we talk about atoms or crystals. The first thing is you need to know the name. Now, if we use our example of water, obviously water is the name of that element. You also have stuff like ammonia, ethene. Obviously, chemicals have certain names. You need to know the chemical formula. For our example of water, that will obviously be H2O. It is very important to note that the formula is not the same as the crystal structure. Okay, a very easy example of this would be something like water. Liquid water is made up of a whole bunch of these, just floating randomly. Solid water, ice, is made up of a lot of these, sitting like this, with another one going there, another one going there, and you have it forming a crystal lattice. So in addition to knowing the chemical formula, you also need to know what the structure is. So I'm going to write the structure or crystal. An excellent example of this would be something like a diamond, for instance. Diamond is carbon, so the chemical formula is C, and the chemical structure of a diamond looks something like this, with the little black balls indicating carbon. Now, as you can see, this is relatively a complex bond, and this is, by the way, an example of a covalent bond. You also have something called graphite. Graphite is the tip of your pencil, very obviously a lot softer than a diamond, and that looks something like this. So graphite is carbon, C, so is a diamond. So just because something has the same formula does not mean it is going to have the same crystal structure or even the same name. that is very important to keep in mind. In addition to this, you need to then also have an idea of how it actually looks. It is a sort of redundant to tell you that you need to know the crystal structure and you need to know how it looks. But an example of this might be something like butane. Butane is a carbon compound consisting, let me just do this, C4H10. So it has 4 carbons, and then it has hydrogens all over the place. Now, we have the name, butane. We have the chemical formula, C4H10. And we have this idea of its structure. But if we actually have to build a model, it is going to look something like this. It is not going to be a perfectly straight chain. So it is very important that you have the knowledge to distinguish between a crystal structure, or in this case the chain of carbons, and how the actual molecule made up of the atoms looks. Not everyone has access to these models, but I have found that for me at least, it very often helps to build something like this. Diamond being a very nice example, one might now understand that this little pyramid, we have another one sitting over here, another one over here, another one over there, and this is the bottom of another one sitting. So it really helps one to visualize and see how these things look if you have access to these models. Those 4 things are the most important things that you need to know when we talk about crystals and lattices and how atoms and molecules sit together. Now, of course, you have different types of crystals, different types of lattices. I mean, this would be a single chain, this would be a 6-sided ring, a hexagon. You've got cubes, you've got tetragons, you've got monoclinic, you've got lots of different structures that they can bond in. I would advise you to have a look at some of those different structures, but please do bear in mind that we are doing this in terms of chemistry. I mentioned earlier that the rocks and the crystals, it is very common to find pages depicting the crystal structures of rocks and such. So please do not go too deeply into those, because we are looking at this in terms of chemistry, not in terms of rocks or minerals. If you are able to do these things, give a name, a chemical formula, a structure, and have some understanding of how the actual compound looks, then we are well on our way to moving forward. This, of course, is important because we are going to talk about chemical change next. Our next topic of discussion will be chemical change. Now, before we can discuss how chemicals change, we do need to understand how they look. For instance, continuing our example of water, we cannot talk about how water changes from a solid to a liquid to gas and the phase changes and what those involve if we do not have any understanding of how water looks and how the molecules and atoms sit together. So even though this work might not seem particularly challenging or even particularly interesting, it is tremendously important moving forward for the physical sections of our chemistry. Ladies and gentlemen, if you have any questions, you are of course more than welcome to comment, and I will do my utmost best to answer. But that is the end of our discussion for today. As I have said, the next time we see each other, we will discuss chemical change. Until then, ladies and gentlemen, have a good day.